Welcome back. This is Computer Science 3, CSCE 310. And today we're going to start on our second to last topic, which is dynamic programming. So let's go ahead and get started. So dynamic programming, the term sounds like it's fancy. I mean, dynamic, right? It's given a lot more credit than maybe it deserves. In that the actual problem-solving technique that we know as dynamic programming is nothing more than an application of some techniques that are very familiar with, that you're probably already very familiar with. In fact, if you look at the history, the term dynamic is actually quite meaningless. It was just a fancy marketing term, right? I believe that the guy that came up with it, or the term at least, and the idea, and he was trying to sell his research basically, and get funding for his research, and so he did this he had to give it a fancy name in order to make it sound important, and so there's really no meaning behind the term dynamic programming. The basic idea is just nothing more than things that you're already familiar with. It's a divide and conquer approach. Approach to problem solving, right? Typically, it involves some sort of a recurrence or recurrence relation, but the idea here with dynamic programming is that you eliminate redundant recursion with memoization. Now, you probably you might have seen memoization before, say in Computer Science 1 or maybe even 2. It's not memorization, it's memoization. It's just another fancy term for something that's little more than caching, right? In other words, you don't want to, the typical example that's given is the Fibonacci sequence. So if you do the recursive version of the Fibonacci sequence, then you end up doing the same function calls over and over and over again. Why do that redundant work when you can do it once, cache it, store it in a table, and then reuse it if necessary? And that's what's called memoization, right? And then the dynamic programming takes it one step further, and you eliminate the remaining recursions by identifying a tableau, right? Again, another fancy name for a table, and filling it out, right? So I'm not going to use the fancy terms. I'll probably call it a table. I'll probably call it caching instead of memoization, et cetera, et cetera. Once you demystify it, you think, well, okay, that's simple enough. That's very useful, yes, but there's nothing dynamic about it, right? So what we're going to do is we're going to do a motivating example here, computing binomials, right? And in fact, I even have this not as a dynamic programming problem, but I typically assign this in a Computer Science 1 course where you use memoization to compute binomials. So just again, it's something that you're familiar with. There's a straightforward solution. A binomial coefficient comes from a binomial expansion, and all we're really talking about is the choose function, right? Consider n choose k. Now, we've already looked at ways of generating subsets of size k. But what I want to do now is I want to consider just computing that value, n choose k. There's a straightforward solution, of course. And that's simply the identity, right? The usual identity that you come up with n choose k. It's fraction n factorial over n minus k factorial k factorial, right? So let's go ahead and program that. I've already got it set up here for Python. I'm reading these in as command line arguments. I'm pulling in the math library so I don't have to write my own factorial function. So I'll just go ahead and compute that directly. Math.factorial of n divided by math.factorial of n minus k times math.factorial of k. There we go. And I'll go ahead and print it out. In fact, I'll be fancy about it. Str of n, choose str of k. And I'm sure that there's a much better, the printf style of formatting in Python would have been better for me to use here, but I'm already committed. Str of r, right? There. I think that's good. Let's go ahead and run that. Python 3, and this is demo. Oh, I need to provide command line arguments. So 10 choose 5. I don't know if that's correct. Let's go ahead and verify that. 10 choose 5. Right. And it's good. Yep, 252. Let's go ahead and try something very large, right? Or moderately large. 100 choose 50. Now this is 100 factorial on the top, and then a lot of stuff gets canceled on the bottom. And it looks like, I don't know if Python is actually computing that accurately. Certainly not the lower order digits there. 100 choose 50. Let's see at least if the higher order of terms, yeah, 10089. So it's getting the higher order terms there, and of course it's getting the scientific notation there correct. But we are losing precision down at the end, probably because it's using it's converting this over to a floating point value rather than an integer. So if we really wanted to compute the actual accurate value, we'd probably have to roll our own factorial function. And in fact, if we do that, I would write a loop that computes n factorial, but not only down to n minus k instead of down to 1. N times n minus 1 times n minus 2 ... n minus k, and that's where I would stop. I wouldn't go further down to times 3 times 2 times 1, because that's ultimately going to cancel out in the denominator down here. I would then compute the factorial and maybe even on the fly cancel things out so it doesn't get too big. But it is what it is. And I got an answer pretty dang quick, right? Well, an alternative way of doing this that is often presented is a Pascal's identity. Right? Oops. Identity. There we go. And I'm just going to cut and paste it because I don't want to have to type it all out. So n choose k can actually be recursively computed as n minus 1 choose k minus 1 plus n minus 1 choose k. Right? So let's go ahead and put this into action over here. There are some base cases. For example, let's see which base cases do I want. That n choose n is equal to 1, which is equal to, and I'll go ahead and there we go, which is also equal to another base case that we're going to use is choosing 0. So n choose 0, right? Is equal to 1. So both of those are equal to 1. And it makes sense because if you've got a subset of size n and you have to choose all of them, there's only one way of doing that. You choose everything. If you have a set of size n and you choose 0 of them, there's only one way of doing that, and that's the empty set. Okay, so those are our two base cases over here. I'm going to go ahead and replace this with a recursive function that basically implements these things. This Pascal's identity here, and then this base case. So def binomial, and we'll take n and k as inputs, and we'll check for our base cases. If n is equal to k or k is equal to 0, then we can immediately return a value of 1. Otherwise, we'll go ahead and return a call to binomial of n minus 1 k minus 1 plus binomial of n minus 1 k. Okay? So let's see if this works. N and k. Same command line arguments over here. So I'm going to go ahead and run that for 10 choose 5. That works. All right, let's try some other cases here. Choosing nothing, that should be 1. 10 choose 1 should be 10. And likewise, because of the symmetry in the binomial coefficients, 10 choose 9 should also be 10. We can try a couple of other things. 20 choose, I don't know, 10. Okay. 184,756. Let's make sure that that works. 20 choose 10. And you saw it as a preview. Yep. Okay, I'm pretty confident this works. So let's go big. 150. All right. All right, I'm going to go ahead and wait for this to run. I'll be back. All right, I let that joke go on too long. Sorry. I'm getting impatient here. Let's go. We saw that execute like almost immediately, right? 50 over here in Wolfram Alpha, minus of course the all the ads and crap that they sent back and forth over the internet here. They were able to calculate that pretty darn quick. Why aren't we able to calculate it over here? Right? And it's because there's going to be a lot of redundancy. So what I'm going to do is I'm going to demonstrate what's actually happening under the hood here with a function count. Func count. Right? This counter is going to be incremented every time we call this this function. So it's a global variable, so I have to say global func count, and then func count is plus plus. Right? And in addition to reporting the actual binomial value there, I'm going to go ahead and print number of function calls. Right? Oops. Func count. There we go. And we'll start small again. Maybe it's just 10, choose 5 here. Oops. All right, you can't do that in... Fine. There we go. All right, fine. There we go. So 10 choose 5 to compute 252 required more than 503 function calls. Okay. What else were we able to successfully compute here? 20 and 10. All right. To compute 184,000 required almost more than double or so, function calls. So we're basically making for each one of for each value for each subset, basically, we're making 2 function calls or thereabouts, right? So what about 100 choose 50? If I do this, then I'm making that many function calls, right? In fact, twice that many function calls. That is going to take me centuries upon centuries upon centuries. No, it's not going to work. Why are we making so many function calls? Right? So what I'm going to do is I'm going to change this function count to only count the number of times we make a function call to say when n is 3 and k is 2. Right? So if n is 3 and k is 2, right, then I'll go ahead and increment this. Right? That's one value. Right? Let's go ahead and run that again for small values there. The number of function calls when n is 3 and k is 2, I made 24,000 calls like that. Why? You compute the value once, you store it off, and then you never have to compute it again. Or you can look it up if you need to look it up, right? Why make 24,000 function calls to compute and recompute this entire thing? So the idea here is that of using memoization would be to use a table, right? That we pass into this function, and we would look at that table and say, have we computed this value before? N and K, we're given N and K. Is that value stored in the table? If so, we'll go ahead and use it. If not, then we'll go ahead and pay for the recursion. When we pay for the recursion, instead of immediately returning, we'll go ahead and put that into the table so that anytime anybody else calls this function on the same N and K, we don't recompute it, right? That's the idea behind memoization. We're not even going to use memoization, though. You don't have to do any of that stuff. You could start from scratch, not from scratch, but you could start by not doing recursion at all, right? So the way that we're going to do that is we're going to set up a table, right? This table is going to run for values of k from 0, 1, 2, 3, 4, ... up to k, right? In fact, I'll leave enough room there. K minus 1 up to k. And then n is going to run from 0, 1. In fact, these are just i's and j's. All right? So I is going to run from 0, 1, 2, 3, 4, all the way up to, up to k. And then we run beyond that, ... n minus 1, n minus k. Or n, just n over here. Okay? There's my table. All right? And what I'm going to do is I'm going to fill out this table. Well, first of all, what about those base cases when n is equal to k or k is equal to 1? So when k is equal to, 0, when k is equal to 0, all of these in this column here are going to be 1s. ... 1 and 1, ... Right? When n is equal to k, then we're looking at the diagonal of this up to this point right here, k. So 1, and it's not drawn to scale, obviously. 1, 1, 1, 1, ... down to there. Right? And it's again, it's not drawn to scale. Which value am I interested in? I'm interested in this value down here, which is n choose k. Right? Now, what does Pascal's identity tell us the relationship to this cell in this table over here? What's its relationship to the other cells? Right? And by the way, these cells up here, 2 choose 4. If I have a set of size 2, I can't choose 4 things from it. So everything up here is invalid. If you want to, you can just go ahead and zero them out, or nil, or infinity, whatever you want to put up here. Everything up here in this region is ignored. Ignore it. These are the values that we're interested down here. Well, n choose k, remember Pascal's identity. N choose k is going to be equal to n minus 1, k minus, choose k minus 1. N minus 1, that's one level up here, one row above. K minus 1, that's one column over. So this is n minus 1, choose k minus 1. What about the other one? N minus 1, choose k. So n minus 1, again, up one row, choose k, same column. N minus 1, choose k. Right. To compute this cell right here, all we have to do is look at the 2 previous cells, one above it and one above and to the left, and add them together. Right? You could start to fill this out too, right? And start to see maybe a pattern here that if I had 3 here, this would be 1, 3, 3. If I have 4 here, that would be 1, 4. Again, all you have to do is, what's the value here? Well, I look up here and add this one. So this is 6. I look up here and add this one. So 4. And then I reach my diagonal at the end there. Right? Hopefully this starts to look familiar to you. Right? If I drew it like this, this is Pascal's triangle right here. Right? Doesn't go all the way. but it looks like it looks more like a triangle. You then draw it over like that to show that it's Pascal's triangle, right? That's why it's Pascal's identity. That's how you formulate Pascal's triangle. All we have to do then, instead of making recursive calls, starting down here and making a recursive call to these two and using memoization to make recursive calls, make recursive calls, make recursive calls, and then fill out the table. So start here, go all the way down, and then fill it all the way back up. Let's cut out the middleman because that was extra steps. Why don't we just start at the top, right, and fill out this table top to bottom, left to right. Right? That cuts out the recursion entirely. All I need to do is start for I running from 0 up to n, for j running from 0 up to k, fill out these tables. Actually, we don't want to go all the way up to k. We just want to, if we start at, say, 2, we only want to go up to 2. So our inner loop only has to go halfway here, and then we could go all the way if you really wanted to, but everything over here would be invalid. And then stop and report this value right here. Right? So let's go ahead and try it. Right? Let's go ahead and try a solution that doesn't have recursion at all. Right? There won't be any function counter anymore. So let's go ahead and create our table here. That's a good question. Python 2D array. Yeah. Okay. This might come in handy, but otherwise, I think it's probably just going to be pretty straightforward here. I don't have to create one, do I? Okay. Let's go ahead and create. What should we call this table? I don't know. B for binomials, or maybe P for Pascal's triangle, right? Yeah, sure, P. Let's go ahead and do this. Normally you'd have to initialize, if in another programming language you'd have to initialize these things, but I don't think you have to. This is going to simply be a list of lists, basically, right? So let's go ahead and I think we could just, yeah, I think we could just treat it like it is, and later on we can print it out. I think we can print out the first row, of course. Can we pretty print the entire thing? I'm not sure. If anybody is more well versed in Python 3 at least, please let me know. Otherwise, we'll go ahead and push through here and see what it looks like. So again, all we need to do is establish two loops here. For I in range of 0 up to n, and so we want to be inclusive on that n because we do want to compute that last value. So a range of n plus 1, right, because it'll go 1 less than that. We're going to run j from 0 up to and including I for j in range I plus 1. Right? We're adding 1 because we need to go up to and including I. And again, that's the diagonal. Along this diagonal right here, that's when 0, 1, 1, 2, 2, 3, 3, when I is equal to j. Okay? And what we'll do is we'll check if I is 0, right? If j is 0, right? Yeah, okay. If j is 0, or if I is equal to j, then we will set piece of ij equal to 1. Right? That takes care of this vertical right here and this diagonal at the same time. Okay. Otherwise, piece of ij is equal to piece of and then this is Pascal's identity, I minus 1, j minus 1, plus piece of I minus 1 and j. Right? There we go. Now let's see what it looks like. Print p. Right. All right, so we are going to have to probably initialize these things. So P is equal to piece of, sorry, I is equal to a new list. I don't know, maybe there's a better way of doing this in NumPy. Okay. So P dot append, and then we can append a list. All right, any suggestions? Otherwise, we're going to have to, we can do range of n plus 1. We can do list comprehensions. It's going to be x, okay, let's look it up. All I'm seeing are hard-coded initializations rather than a dynamic initialization. You should be able to just do this. Python 3 2D arrays. I don't want to bring in NumPy. All right, fine. For I in range n plus 1, P is equal to this. P sub I is equal to range. We'll end up overwriting all these values anyway, plus K. I think I can do that, right? Line. We're going to have to append then. This is stupid. No, I don't like that. So let's back up. All right, fine. You want to, each one is going to have to be, darn it. All right, nobody's suggesting anything? I think we are. Remember, we're live on Piazza Q&A here. Darn it. How do I get, so this is the list. P sub I is equal to a new list. I should be able to do that, right? No. Maybe a list comprehension. No. All right. I'm about to ready to give up and move on, or maybe just use NumPy. Let's see. Should be a way to do. Fine, we'll use NumPy. P equals np dot ones, and we'll end up overwriting most of them anyway. Of n plus 1, k plus 1. There we go. And I need to bring in NumPy. Import NumPy as NP. Nope. It's not liking that either. Ones. Oh, the duh. There we go. Darn it. Anyway, I thought we could do it in Python. I was going to do it in over. Oh, here we go. Yeah, I think I tried that under the first for loop. So, good suggestion here. Append a list right here. Let's go ahead and try it really quick. Oh, P dot. Oh, okay, fine. Well, P. Oh, hopefully. Thank you. If this does work. Now, list index is out of range. So, oh, maybe just P dot append. Because it's already a list, right? Yeah, all right. I'm ready to give up, but I'll go ahead and look at a better solution and post it later on if we want to. But otherwise, trust me, it would have led to an instantaneous solution, just like Wolfram Alpha here. Right? That here, that 100 choose 50, and it would have all been native integer types, and so we would have actually gotten the accurate result here, likely, right? Rather than using the math library's factorial function. Okay. So that was my attempt at an exercise to show you how you go about dynamic programming. Let's go ahead and identify what I did, at least the basic steps that I performed along the way. We identified a value that represents the optimal or actual value of a problem. We're going to be looking at optimization problems, finding the best solution rather than just a solution. Binomial coefficients aren't finding best solutions of anything. They're just computing a value. But in general, you would want to find the value or establish what an identity that represents the best value that you want. Right? You identify a recurrence identity in terms of values to smaller problems, right? And we didn't do this. Pascal did this several hundred years ago. He came up with Pascal's identity. So it's solving this n choose k problem in terms of smaller binomial problems, right? That n minus 1 and k minus 1, n minus 1. That's making progress towards the smaller conditions of the base cases here, the trivial cases of choosing n or choosing 0, right? The trivial cases. You prove your recurrence is correct. This is something now. This goes beyond the scope of this course, but in general, you do want to do this. And basically, they have another fancy term for this. This is the optimal substructure property. Right? It's just a simple application of induction. Right? So all you have to do is, because it's a recurrence, all you have to do is use induction. Show your base case. Show that the left-hand side is equal to the right-hand side. Assume that that's correct for k. Then you show that that implies that it's correct for k plus 1. Not the same k in this case, though. Okay. But that goes beyond the scope of our attention. We're just wanting to use it as a problem-solving technique. Right? All right. Nobody has any solutions for our program. So if anybody does have a suggestion on how to improve that program, maybe we can get it done today. Otherwise, you identify trivial base cases, right? Where there is no solution like we did over here. So you could also call these base cases where it's invalid, and so you ignore them, and you can fill out those base cases. But the real base cases that we used here were the column and the diagonal, right? So you identify trivial base cases and their values. You identify the desired final result, right? Where that is, right? What value is that? And that's down over here in the bottom right of the table. Not all tables are going to look like this, but you will eventually have a table or a tableau where you would need to identify that. You then identify how you set up a tableau that holds values to sub-solutions. And oftentimes this is going to be like Floyd-Varshall's algorithm. Not only were we keeping track of the distance of the shortest path, but we were also keeping track of the successor or the predecessor vertex, the successor vertex, because we actually wanted to come up with the solution later on. With this example that we were looking at before, all we were doing was we were only interested in a value, not the actual subsets that correspond to that value. But sometimes you will need to keep track of additional metadata, and for the examples that we're going to go over, we will be doing that. You set up a tableau that holds values to sub-solutions and possibly additional data to reconstruct solutions. Right? Then, once you've set that out, you fill in cells corresponding to the trivial base cases. You identify the final the cell corresponding to the final result, right? Final desired result. Once you've set up your table, then you need to figure out how things relate to each other. You identify how cells relate to each other. And again, that's just going to be the recurrence. In the way that we did it over here, we said, well, oh, this is the desired value, and it's dependent on the one right above it, and the one right above it and to the left. Therefore, if we want this value or any value in this, we have to fill it out left to right, top to bottom. So once you've identified how cells relate to each other, then you can write your for loops, right? You can fill out cells in the table in an order so that needed values are cached. And they were all cached. I mean, technically speaking, you could get away with one row in this table, right? The previous row, and then you fill out the next row, and the next row will only be dependent on that new row, so you can throw out that other row and continue. So if you really wanted to optimize, you could get away with, instead of a two-dimensional array here, you could get away with a single-dimensional array. That might be a way that we could change this. I'd have to swap out the old array with the new array. I don't want to do that. That's even more error prone, at least without having done it before. So here, suggestion for the matrix. All right, I'm going to cut and paste your solution there. There. So let's walk through what he did, or what she did. For I in range n+1. P dot append, we're going to append, okay, good. And then for J, in that you append another, okay. Let's go ahead and try it out. Did I change it? Oh, okay, I'm going to get rid of this because that sets me up entirely. Thank you. Still out of range. I, J. Should it be J there? No. Darn it. Shouldn't be that hard to have two-dimensional arrays in Python. Right? But in any case, let's go on. Right? So that needed values are cached. Right? So those are the basic steps, right? And I'm putting a lot more detail in there, but that's what we did. That's what we did here. Okay. So what I'm going to do for the rest of the time is, in fact, we're going to look at 2 more problems that lend themselves to dynamic programming solutions. One of them I'm only going to talk about very, very tersely, and then we're going to look at another one in detail. The first one that we're going to look at is optimal binary search trees. All right. This is the one that I'm not going to go into too much detail here, because last year I pre-prepared a bunch of video slides or video lecture. I think that there are 5 lectures there that I'll post again. I used Lightboard last year, and it turned out pretty well. I was just putting that together as an experiment to test out Lightboard. And so I'll ask you to watch those videos for the full treatment of optimal binary search trees, for all the details, basically. But here's the scenario, right? So we want a binary search tree because we've got keys that we want to look up. But we also have additional information about the things that are stored in this binary search tree. We know, for example, if it were a search engine kind of thing, where like Google, where somebody is searching for sports, right? They search for baseball. That's going to be very, very common search. But football is even more popular, at least in the United States. American football is more popular in general. And so that search result is more likely, right? Whereas if you search for shinty, if you've ever heard of that, that's probably going to be very, very low on the search scale. It's going to be very, very uncommon, except for when somebody mentions what shinty, and then everybody runs to Google to find out what the heck is shinty, right? So optimal binary search trees. The scenario here is that each key has a probability of being searched for. For example, let's just go ahead and have keys A, B, and C. And the probability of that key, let's just say that it's 0.6, 0.3, and 0.1, right? In other words, 60% of the time people are searching for A, 30% of the time they're searching for B, and only 10% of the time they're searching for C. So football, baseball, hopefully that's a lot higher, and shinty, right? It's probably not that high, right? So let's go ahead, and these are ordered, right? A comes before B, comes before C. So we need to enforce the binary search tree property, but we also have this additional information that we can take into account. So what kind of binary search trees could we formulate? Well, if I ran, say, an AVL tree or a 2-3 tree, or no, not a 2-3 tree, yeah, a 2-3 tree could result from this, and I try for a completely balanced tree, right? Then what is the average number of comparisons overall, right? To search for these things. Well, for B, if you're searching for B, it only takes you one comparison, right? And you're only searching for it 60% of the time, right? 0.6. So on average, you are making 0.6 key comparisons in order to search for B. Right? What about A? A has a depth of 1. So if you're searching for A, you would make one comparison to see that, oh, that's not it, that's B. I need to go to the left subtree. And you'd make a second comparison here to see that that is indeed what you were searching for. So to search for A requires 2 comparisons. Likewise for C, it requires 2 comparisons because you'd find it on the other side. Those are not the probabilities. The probabilities here were 0.6, 0.3, and 0.1. So 0.6, 0.3, and 0.1. Now, when I multiply these all together and I sum them all up, I get that it's 0.3, 1.2, so 1.5, 1.7, yeah, right? key comparisons on average to search for everything in this tree. Now, if you're searching for something that doesn't that's not in the tree, then that's kind of out of the scope, right? Then then that shoots up the number of. You'd have to define a probability of an unsuccessful search in order to incorporate that into this, right? That's one example. Can we do better? Remember that was 1.7. Right. What if we drew our tree like this instead? Completely unbalanced. In fact, if this were an AVL tree, what kind of rotation would it have to be to get it balanced again? A right-left rotation. Right? What is the average average number of key comparisons to search in this tree? A, B, and C. Now A requires 1. C is at depth 1, so it requires 2 key comparisons, 1 with the root and 1 with itself to stop the searching. And B requires 3. Remember, it was 0.6, 0.3, and 0.1. So all together, when I sum these all up, it's going to be 0.6, 1.9, 1.5, 1.7. Oh, okay. Same thing. Right? So maybe we can't do better? Oh, there are lots of binary search trees with just 3 keys, right? You could, in fact, they correspond to all the rotations of an AVL tree that we looked at. There's a perfectly balanced binary search tree. There's a tree that is all skewed all the way to the left, a tree that is skewed all the way to the right, a skewed tree to the right, then left, and a skewed tree to the left, then right. Right? In fact, there are 5 possibilities with just 3 keys. Let's try this one. A, B, C. Skewed all the way to the right. Now I've got A being 1 comparison, B being 2 comparisons, and C being 3 comparisons. Right? Basically, I just swap these out. 0.6, 0.3, and 0.1. When I multiply all these together, I come up with 1.5, which on average is even better. Right? So if we have additional information here on the probability distributions of searching for something, what we can do is we can build a custom tree for those search terms or for those keys with that is going to minimize the average number of key comparisons. Okay? So how do we do that? Well, again, I'm not going to go over all the details here because that's in the video series that I've already prepared, and I'm just going to go ahead and post those to Piazza and Canvas. But here's visually the idea, right? If you are given keys K1, K2, ... Kn, right? Then the way that you start this out is by saying, well, what's my this is the divide and conquer kind of approach. What if I used a particular key as my root, right? That's basically what we did with before. We said, well, what if this key was the root, and then everything else, everything less than it went on to the other side, and everything greater than it went on to the other side. So let's just say that K sub L. I chose one of these keys to be my root. It could have been this one, and then I skew everything to the right over here, or it could have been this one, and I skew everything to the left. But let's just go ahead and say that in general it's in the middle somewhere. This is a tree, and this is a tree. Oops. This tree contains keys K1 up to KL minus 1, and this tree contains keys KL plus 1 up to Kn. Right? And now all I have to do is come up with a recurrence. Right? Let's C sub I j. Right? I'm going to let that be let that represent the optimal the average number of key comparisons in an optimal binary search tree with keys k sub I through k sub j. All right. I'm keeping it general here because I don't want to just consider 1 through n every single time. eventually, when I come down here and I want to ask what's the optimal configuration for this subtree? Well, my keys are going to be different, right? They're going to be in general, they're going to be I through J, right? Some subset of some subsequence of these keys up here, right? So what are some obvious corner cases? C sub, say, I don't know, 0. Oh, here I know. C I, right? In other words, what if you just had one key? There's no choice, right? This is going to be 1 times the probability of searching for Ki, the ith key. Right? Why is that? Well, if I've only got one key, then there's only one configuration. It's a node by itself. And it takes one key comparison to verify that this is the key that I'm looking for. We called that a seed, right? It's a tree of size 1, right? You also have other quarter cases here that C sub I and I minus 1 is equal to 0 because this is invalid, right? If I'm looking for I through J, but if I've got those flipped, right, and I'm looking for, say, key K 2, 1, right? The keys involving 2 through 1, that's backwards. And so that's invalid, and we say, well, it's 0. That's just one of our corner cases. That's one of our base cases. Which value are we interested in? Well, we're interested in the tree containing all of the keys, so 1 through n. You follow the process, and you come up with a table that looks something like, the following. Oh, sorry. What we need to do is then we need to come up with another the actual recurrence. We identified what we wanted. We identified the base cases. What we actually need to do is we need to identify the recurrence, right? So if I've only got I through J, that's QI, KI through KJ, right? Then again, I need to ask the question of which key is the root. And then that'll break it down. Say that it's KL. Well, that means that everything else goes over here and everything else goes over here. I've got a lot of choices there. It could be I plus I. It could be I plus 1. It could be ... It could be J. Right? So which one do we choose? We choose the best one. We choose the minimum. I want to make sure I get this right. Yep. Of all those possibilities, L being I, L being I plus 1, I plus 2, ... all the way up to J, of C sub I, L minus 1, plus C sub I, L plus 1 up to J. Basically, I'm just I'm cutting the keys in at K sub L, and then I'm putting I through L minus 1 over here. I'm putting L plus 1 through J up here, and whatever the optimal value for this subtree plus the optimal value for this subtree plus the cost of combining them into one new larger tree. That cost is simply going to be a sum of probabilities of all the keys. And I've run out of subscripts here. This is an S. S is going to run from I up to J. Right? So again, what is this doing? Well, I'm taking this tree, and I'm combining them by creating a new root node, kind of like you did with Huffman coding. That necessarily makes this tree one level deeper, So if I had to make a certain number of key comparisons over here, well, now I have to make one additional key comparison, and because everything is lower in the tree now, I have to make one additional key comparison for everything in this tree, and as well as this key, and as well as everything in this tree. And that's just simply a sum of all the probabilities. Right? The metadata. So all we need to do is come up with a table now that represents all this stuff. And I'm going to leave that for the other videos, right? Because again, I've got a 5-video series that goes through that, goes through setting up the table, goes through the pseudocode and an example of filling out the table, and then also keeping track of the metadata, because you have to remember which key did I choose that gave me the optimal solution, because I need to rebuild that tree, and this is what you're going to program eventually. You need to rebuild that tree, so you need to know, given these keys, oh, this one is my node, my root. So I'll recursively go down here and build this tree, or recursively go down here and build this tree. Again, I'm not a fan of recursion, so I present it as a stack-based solution instead in those videos. Okay? All right. With the remainder of our time today, I just want to introduce the other problem that we are going to look at. And in fact, you've already seen the problem before. I want to remind you of the 0-1 knapsack problem. All right. The 0-1 knapsack problem is you are given n items. All right. And I'm going to be more concrete about it and just give you the instance that we're going to use here. A1, A2, A3, A4, A5. Remember, you're a thief. These are the items. They have a certain weight. The weight here are going to be 5, 2, 4, 2, and 3. And here's the value. I'm reviewing this because in years past I haven't had to review this because you've programmed it. I think I cut that out in favor of the click problem this year. But you're given n items, each with a weight. And a value. Right? You're also given a capacity, W. In this case, what is our capacity? I don't know what our... it doesn't matter. I'll just say that we have a capacity of W, say, is equal to 10, right? And then we'll come back and maybe there's a different capacity that we can look at. In fact, if I said that the weight capacity is 100, guess what you can do? 5 plus 2 plus 4 plus 2 plus 3. You can carry all of this stuff. So steal everything. And you have an optimal value of 1537, right? What if I said that you have a capacity of only, I don't know, 2? Well, now you can only take this item or you could take this item. You couldn't take anything else because once you take one of these 2 items, you've reached your weight capacity in the 0-1 knapsack problem. You can take something or you can take something or you can leave it, right? But once your capacity is full, you can't take anything else. So the optimal solution there would, of course, be take the more valuable thing if you can only take 2 things, right? What if I had a weight capacity of, I don't know, 20? No, let's go with 8. Right. Well, if I'm going to be greedy about it and I start taking the thing that is the most valuable, then that means I'll take A1, right? Now I've only got 3 more pounds that I can carry. Okay, I'll take the next valuable thing. Well, I can't take A3 now because that weighs 4. So the next available valuable thing that I can carry is this one, A5, and that gives me a total of 17. Right? Can I do better, right? Or not? Right? So here's the idea, and this is what we're going to develop today and go over maybe more details tomorrow. Right? Okay. We're going to have to define a recurrence, and darn it, what is the capacity for my example? Oh well. I'll go ahead and look it up and get back to you tomorrow. Right? So let's go through the process that we identified over here, where we identify a value that represents the optimal solution first. Okay, so that's just an equation basically. V sub I j. We're going to define this as a value that is the optimal solution to the 0, 1 knapsack involving items A1 through AI, right, with an intermediate capacity J. Right? That's the first step. I'm just defining that there's this there's this equation that will give me that answer. In fact, let me move this over here. Now we need to identify a recurrence identity in terms of values to smaller problems. We won't prove our recurrence is correct, but we'll identify trivial base cases, and we want to identify also the desired result. Oh. Ooh. All right, you can hear the air raid sirens, which means it's time to take a break. And here's another suggestion. Let's go ahead and try this. Very good. I don't know how well you can hear that or not, but it's Wednesday, obviously. That is a good list comprehension right there. And then, yeah, let's go ahead and try it. Yeah. Where? I saved it, right? Line 30. Okay, I must not have saved it. Sorry. Line 14. Oh well. J. Maybe I've got my range wrong there. Oh! That must be it. Thank you. No, we only want to go up to I. But, well, okay, we could go ahead and try this. And it's still going to be out of, yeah, we're going to have a problem with this. But in any case, there's the answer right there. Let's see. Why am I not? Oh, R is equal to P sub I, not I, but N. Okay. Yeah, there we go. And I don't immediately see what my problem was, so thank you, anonymous mouse. There we go. And we can also do large values 150. Hey, all right. Is that right? What do you say, Wolfram Alpha? Yeah, okay, good. Thank you for the solution. And again, the solution here was a nice list comprehension for initializing everything. I think that you just made it big, and then then you did go up all the way, filling that out with maybe zeros or something. Yeah. Okay. All right. In any case, let's go back to this. All right. Again, V sub ij is going to be the optimal solution to the 0-1 knapsack problem, only involving elements 1 through I, not all the elements initially, and with an intermediate capacity of j. If we do that, then we can identify the trivial base cases here. As that winds down. Okay. So V sub 0j, right, is going to be 0 for all j. What is this doing? It's the optimal solution to the 0-1 knapsack problem involving items A1 through A0. In other words, no items. Now, the capacity is irrelevant because you're not taking anything. So you're being a good person and you're not stealing anything. Right? V sub I0 is the other trivial trivial base case solution, because for all I, there's no capacity. Right? If you have if your knapsack capacity is 0, then you can't take anything. Your arms are broken. You can't carry anything at all. Right? So it doesn't matter. You can't even carry the knapsack anymore. Right? Okay. those are our two base cases. What we need to do now is we need to come up with the recurrence. What's the identity? What's the desired result? This is the final value of the solution, right? It involves. Oh, sorry, no, not that. NW, right? V sub all the items and then our capacity. I think I identified it as W. There we go. This is the final value of the solution with involving all elements. And that doesn't necessarily mean that you took all elements. It just means that you're considered all of the elements with capacity W, right? Now, the last thing that we'll do today, well, maybe two more things, is come up with a recurrence. Right? How do I get a hold of V sub ij? Right? So, case one. You can separate everything into two groups. You can separate it as suppose that you do not take item a sub I. Right? So if you're not taking item a sub I, then it's not going to affect your capacity, and you just have to look at the value v sub I minus 1 j. Choosing not to take I means that you do not. It doesn't affect your capacity because you're leaving it on the shelf, and you simply look at, well, then what's the optimal solution with all the other items that I've considered so far, right? Case two. You do take item a sub I, right? Well, if you take item a sub I, then you've gained its value, but you have to carry it, so you've changed your capacity, right? So what I mean by that is you add the value, you gain the value v sub I because you've taken item a sub I, but you decreased your capacity, right? Whatever the capacity was before, J, has now been decreased by the weight of the ith item, right? So I've taken the item. Now, what's the optimal solution to when you consider all the other items, right? So it's in case two where you do take the item, it's going to be v sub I minus 1. But now you need to adjust for your capacity. It's no longer j, it's j minus wi. All right? But if... Oh, and sorry, plus. Because I gained the value here, v sub I. Right? So whatever the solution is to that other sub-problem plus the value that I've gained by stealing item I. But if j minus wi is less than 0, then taking a sub I is infeasible. Right? You can't take it. Because like we saw in the example, that once my capacity went down to 2 or 3 or whatever it was, I was not able to take the next most valuable item because it weighed too much. Right? So we have to take all of these. These are actually 3 cases here, right? You first have to determine, is it feasible to? You first have to determine, is it even feasible to take it, and if so, should we take it? Is leaving it better than taking it? In other words, take the maximum of this versus this. Right? But of course, if it's infeasible, then we don't have a choice, and we simply have to we simply have to leave the item there. Right? So bringing all that together into one expression, v sub ij is going to be equal to, our first case is v sub I minus 1 j if j minus the weight of the ith item is less than 0, right? This is infeasible. And so we can't take the ith item. Otherwise, it's going to be the max of v sub I minus 1 j, which is the same as up here, because it's infeasible and we're leaving it, but it's feasible, but we chose not to take it, versus v sub I minus 1 j minus w sub I, right? Whichever one of these is the max, right? Leave the item, and this is take, plus, I keep forgetting that v sub I, take the item, right? So you have no choice. Just fill out whatever was in the table before. You have a choice. Should we take the item and add its value, or should we leave the item and not add its value, right? Which is essentially saying that it's the same value as being infeasible. Okay. The last item that we'll do today is we'll draw our table, our tableau. Right? And I like the way I drew it here, so I'm going to do it up here. There we go. All right. So here's I and j. I is going to run from 0, 1, 2, 3, ... I minus 1, I, ... up to n. Right? The columns will correspond to our weight capacities. So 0, 1, 2, ... I'm going to insert j of j minus wi here so that we can illustrate it later on. ... w. Right? Again, this corresponds to not taking anything, considering all solutions where you took the first that involve the first item, considering all solutions that involve the second item ... and considering all solutions that considered all the items. This is our weight capacity. What if we had a weight capacity of nothing, of 0, a weight capacity of 1, a weight capacity ... all the way up to w, right? So what are our base cases? Remember, if we don't consider any items, then our value is going to be 0. If our weight capacity is 0 because our arms are broken and we can't carry anything, then our value is going to be 0. ... 0, ... 0. So the first row and the first column end up being our base cases. Again, all we're doing here is we're setting up a tableau that holds sub-solutions and possibly additional data to reconstruct solutions. We fill in the cells according to the trivial base cases, which we just did. Now we identify the cell corresponding to the final result. Well, the final result is involving all items with the input value here. So this is v sub n w. That's our the value of our final solution. Okay. Now we need to identify how the cells relate to each other, because I can fill in these trivial cells over here, and I want this value right here because that's the value to the solution to the problem. But how do I fill these in? I need to define how this relates to all the other cells over here. Right? And I shouldn't have thrown that down. Here we go. So there's our solution. V sub I is going to relate to V sub I minus 1j if it's infeasible. Where is that on here? Well, it's one row up. N minus 1, or if I want to look at, say, V sub I, and then say j is over here. V sub ij. Right? I, j. Where do I look? Well, I need to get a hold of V sub I minus 1j. In other words, the same thing in the same column. V sub I minus 1j. Right? Go with a smaller pen here. V sub I minus 1j. Right? That's the same cell that I use over here to determine my max. Or v sub I minus 1, in other words, one row up, but several columns over. And in this case, it's not just going to be a one or two columns over. In this case, it's going to be a variable number of columns over that depends on w sub I. So this is v sub I minus 1, j minus wi. Right? So this value depends on the one immediately above it, and the one immediately above it and several columns over. Okay? That suggests a very easy solution for filling this tableau out. All we have to do is go top to bottom, left to right, just like we did with the binomial coefficients. So all we need to do is for I running from 0 up to n, j running from 0 up to w, fill out that particular cell based on the one above it and the one above it and to the left, right? Of course, it's a little bit more complicated than that because you first have to say, is it feasible or not? If it's infeasible, then you just have one choice. If it's feasible, then you have to say, well, which one of these is the maximum, right? And that's the value that you fill out. We'll go ahead and save that pseudocode for tomorrow, though. All right, and again, thank you for helping me out with my bad Python today.